Hello everyone, my name is Dr. Chen, and I'm a first-year internal medicine resident at Mercy Fort Smith, Arkansas. For today, my topic is polyunsaturated fatty acids, its role in mitochondrial dysfunction, and the development of insulin resistance, diabetes, and obesity. So first, a brief background. Polyunsaturated fatty acid intake has dramatically increased in the last 50 years, and currently the prevalence of obesity and diabetes are 41.9% and 11% respectively. The investment of resources towards combating diabetes alone totals $413 billion, and individuals with diabetes are at a 60% higher risk of death when compared to those without. These statistics paint a devastating picture of the massive burden that the aforementioned diseases have on our society. And in my talk, we'll explore how polyunsaturated fatty acids are an essential driver of these disease states from a biophysiological perspective. With an increased intake of polyunsaturated fatty acids, or PUFA, the percent composition of PUFA within adipose tissue and phospholipid bilayers of cells also increases. This poses a problem because PUFA have a key distinction in its structure from saturated fatty acids in that they contain double bonds. By the chemical nature of these bonds, they are extremely prone to oxidation, and this is especially problematic in mitochondria because of the specific molecule called cardiolipin. Cardiolipin stabilizes the conglomerate structure of the electron transport chain, forms the cristae, and maintains the membrane potential within the mitochondria. It is like a triglyceride, but it has 4 acyl tails instead of 3. More PUFA in the diet inevitably destines its incorporation into these tails. Combined with the constant exposure to oxidative stress from respiration within the mitochondria, the cardiolipin spontaneously oxidizes, compromising its structural integrity and function within the mitochondria, and induces a profound loss of cardiolipin and a concordant reduction in ATP production by nearly half. We see this demonstrated by the work of Ghosh et al., where their goal originally was to prove that PUFA reduces rates of apoptosis, which they were successful, but that was because rather than apoptosis, cells underwent necrosis instead. As in Figure B, you can see that the rats in this study receiving a PUFA diet have a significantly lower cardiolipin level than of those receiving a standard rat chow. Diagram A shows a healthy mitochondria with its intact cristae, where diagram B shows a pathologic mitochondria that has collapsed. It needs to be stressed that mitochondria are subject to these processes only with PUFA present. The loss of cardiolipin renders mitochondria severely damaged, incapable of properly and efficiently oxidizing energy substrates. This results in the accumulation of intracellular lipid intermediates, like in the cardiac muscle of these rats as depicted in Figure C, which here I want to emphasize that the damage occurs independently of ischemia. These processes play a major role in the pathogenesis of insulin resistance and thus diabetes and obesity at the cellular level. And shortly, in Figure D, mice of a diet comprised of saturated fat, stearic acid, have substantially less abdominal fat than its PUFA diet counterparts. In conclusion, excess PUFA in the diet jeopardizes mitochondrial function and subsequently cell energy production. The loss of mitochondrial ability to efficiently oxidize fats contributes to the development of insulin resistance, diabetes, and obesity. So, dietary sources of PUFA should be entirely eliminated from the human food supply. And of course, further research, ideally involving human subjects, would be instrumental in further elucidating the harms of replacing saturated fatty acids with PUFA in our diets. Thank you.